Hello everyone. And so up until now we've been discussing how chemical reaction rates depend on reactant concentration. We explored the dependence of chemical reaction rates on the time of chemical reaction using integrated rate laws in the last tutorial. But we still haven't discussed how it is that temperature affects chemical reaction rates. If you recall, in the very first section of the chapter, we did identify the temperature as being one of those factors that affects chemical reaction rates. And so, for example, let's take this reaction that I put on this slide to start our pre-lecture tutorial. I have some reactant A reacting with the reactant B to give me products C and D. And let's assume that this reaction is actually first order in reactant A. Let's also assume it's first order in reactant B. And so, if that's the case, we get the overall rate law of rate is equal to K times A times B. Now, again, notice that there is no inclusion of a variable capital T, which would actually show a mathematical relationship with the temperature of the chemical system. And the reason for that is because that temperature dependence is actually locked away within the rate constant. It's actually the rate constant that depends primarily on the temperature. Now, this temperature dependence of the rate constant is actually mathematically expressed using an equation called the Arrhenius Equation. So the Arrhenius Equation says that the rate constant K is equal to a factor A, which I'll explain what it is in a moment, times E, so the exponential term E, to the negative EA over RT, where EA is the activation energy. Okay, now essentially, just to sort of quickly review, the activation energy actually represents that small sort of investment of energy, which can be small, I should say, or sometimes it can be rather large, depending on the chemical reaction, such that you go and you actually push the energy state of the reactants to a high enough level to actually overcome this barrier in energy, so that eventually the reaction can proceed down to the products. Now, this investment in energy is what we call the activation energy, and typically this investment in energy is necessary to break existing chemical bonds. Okay, so that's the activation energy. Now, R is the ideal gas constant in its energetic units, so that's 8.314 joules per mole Kelvin, and T is our temperature in units of Kelvin. Now, this factor A that I mentioned earlier, this is something that we call the frequency factor. Now, the frequency factor actually has considerations of two factors, if you will, relative to the chemical system. The first is the frequency of particle collisions. In other words, how often do reactant particles collide with each other? Because the more frequently they collide with each other, the quicker the reaction will probably proceed. In addition, it also tracks the probability of favorable collision orientation. In other words, are the particles, the reactant particles, situated in space in such a way that the chemical reaction that we want actually occurs? Both of these factors are rolled into what we call the frequency factor. And so, much like every other chemical equation or equation involved in the field of chemistry, This can be solved algebraically. If I've been given all but one variable, I can solve for the remaining variable. But as we learned in the last pre-lecture tutorial when we were discussing integrated rate laws, these equations are often more helpful than just simple algebra exercises. And so the Arrhenius equation is actually useful because it can be used to actually determine the activation energy and the frequency factor for a chemical system. And the way that that works is, suppose we have the Arrhenius equation here. I'm going to take the natural logarithm of both sides. So that's going to be the natural log of k is equal to, and this will be the natural log of a times, and the natural log of an exponential is actually just the exponent by itself, and that's going to be negative EA over RT. Now, essentially, there's a property of logarithms that the product of logarithms is actually equal to the sum of those logarithms. And so I can actually rewrite this right-hand side as natural log of k is equal to the natural log of, actually, no, let me rearrange these terms a little bit. It's equal to negative EA over RT plus the natural log of A. Now, once again, you should start to see a trend here. This looks an awful lot like the equation of a straight line, where my y variable is the natural log of k. My x variable would actually be 1 over the temperature. Okay? So if I take the natural log of k and plot it versus the reciprocal of the temperature, I'm going to get a straight line. And that straight line will have a slope of negative EA over R. And since R is a constant, if I get the slope, that means I can easily actually calculate, the activation energy. It's also true that the y-intercept here is the natural log of the frequency factor. And so if I can construct the plot of natural log of k as a function of 1 over t, then I can calculate both the activation energy and the frequency factor from the graph. So that is useful in its own way, but that would mean I would have to actually generate a fair number of points where I measure the rate constant at varying temperatures. Now, if I wanted to sort of take a shortcut, there is a way that I can actually do that where I don't have to actually acquire so many points where I measure the rate constant at different temperatures. If I just take 2 points and do a little algebra, then I can also come up with the activation energy. And the way that I would do that is by using the equation that I just showed you up at the top of the slide, namely this equation right here. So suppose that I have 2 conditions where I will go and I will measure the rate constant at one temperature and then turn around and measure it again at a second temperature. For each of these conditions, the natural log of k should equal negative EA over R t for each respective measurement plus natural log of A. And for the second conditions, the same equation will apply, but with K2 and T2 in place of K1 and T1 in the first equation. And if I subtract each of these equations from each other, what I'm going to get is the natural log of K1 minus the natural log of K2 is equal to negative EA over RT1 plus the natural log of A minus, and this is going to be negative EA over RT2 also plus natural log of A, because since we're still talking about the same chemical reaction, then EA and the frequency factor should be the same, even if we're doing these 2 measurements under different points in temperature. And so if I go ahead and distribute this negative sign then that's going to give me negative EA RT1 plus natural log of A plus EA over RT2 minus natural log of A. So the natural log of the frequency factor will actually cancel out. And on the other side, there is a property of logarithms that says if I subtract two logarithms from each other, that's the same thing as taking the natural log of the ratio of both quantities. So now the left-hand side has become natural log of K1 over K2 is equal negative EA over RT1 plus EA over RT2. Now I can go ahead and factor out EA over R, and also rearranging these terms so that basically the negative term appears second. Basically I would get 1 over T2 minus 1 over T1. And so using this equation, if I have measured the rate constant at two different temperatures, then I should be able to, since R is a constant, I should be able to calculate the activation energy. So let's take an example of this. Suppose that I have a chemical reaction and I've measured the rate constant at 273 Kelvin and at 300 Kelvin. And I have found that from moving from 273 Kelvin to 300 Kelvin, that the rate constant has increased by a factor of 7. So I'm expected to calculate the activation energy for this reaction. So I would use the equation that I just derived. Natural log of K1 over K2 is equal to EA over R 1 over T2 minus 1 over T1. Now notice that the ratio of rate constants is the reciprocal of what I need, because this sentence right here saying that the rate constant increased by a factor of 7, that means that they're talking about K2 over K1 being 7. So probably the easiest thing to do would be to rearrange the equation so that this ratio appears as opposed to that one. As it turns out, that rearrangement's not so bad. Basically what I can do is take the reciprocal on the left-hand side, and all that's going to do on the right-hand side is interchange the respective temperatures. Okay, so these two equations are equivalent to each other. But this was just a little bit more convenient to use based on the way the problem is worded and set up. So what that means is this is going to be the natural log of 7. That's going to equal the activation energy over R. R is 8.314 joules per mole Kelvin. And if I plug in the temperatures, that's 1 over 273 Kelvin minus 1 over 300 Kelvin. So if I go ahead and do the algebra and solve for the activation energy and do the calculation, what I find is this comes out to 49,074 joules per mole. But this is a somewhat larger number. And so I could probably go ahead and convert this to kilojoules per mole, and that would make that 49.1 kilojoules per mole. So we're going to discuss this further in class tomorrow. Work on the follow-up assignment. If there are any questions, by all means email, and we'll see each other in school tomorrow. Have a good night.